Number 17. Translate the phrase into a mathematical expression, then evaluate it. Now notice it's asking us to do two different things. It's so easy to just do the first thing and say, aha, I got it, and then forget to do the second thing, which is easy, right? So the two things are, first it's translate the phrase into a mathematical expression, and then the second part is evaluate it. So let's do both of those things, all right? Okay, so now we have 7 squared. Now remember that when something is squared, it's like a box. Let's say like this one. That's 2 squared because there's 2 on a side. 2 times 2 is 4. You notice there's 1, 2, 3, 4 boxes, right? And then cubed, it says plus 2 cubed. 2 cubed, actually, I can even draw that. Oh, that's not a cube. Well, let's try again. I'm sure this is fascinating. All right. Oh, I connected the wrong thing. Well, it's not a cube. But if it were a cube, it would be divided like that, right? It would be 2 times 2 times 2. 2 times 2 times 2. Cube. Terrible cube. So 7 squared is to the second power. 7 to the second power plus 2 cubed plus 2 to the third power. Something squared is 2-dimensional, something cubed is 3-dimensional, hence the names. Okay, so now 7 squared plus 2 cubed. Easy enough. Now, second part, evaluate. So 7 squared, or 7 to the second power, is 7 times 7, is 49. 2 cubed is 2 times 2 is 4 times 2 is 8. 2 cubed is 8. 2 times itself 3 times. 2 times 2 times 2. 4 times 2. 8. Okay, now 49 times 8 is 57. Our answer. Well, our two answers. That's the translation, and that's the evaluation. Number 18. Provide an appropriate response. So that means what's true about this, what's appropriate. There's a negative 15 to the 6th power equals a negative 15 inside of parentheses to the 6th power. And it says they're equal. Is that true or is it false? Well, let's see. Negative 15, the only thing that's taken to the power is the base. The base here is 15. All right? Here in this case, the base is a negative 15. So in this situation here, it's the 15 going to the 6th power, and then that's a negative. But here it's the whole negative 15 to the 6th power. Now, will that give us a different answer? So let's just write it out and see. So a negative, this could be a negative, I'm going to put it inside a bracket, and then we've got 15 times itself 6 times, right? 2, 3, 4, 5, 6. Alright, now does that equal a negative 15 times itself 6 times? I don't know if I'm going to get that in here. Negative 15, negative 15. I didn't. Alright, I'm going to just put the times though. Anyway, actually we'd have each of these in a parentheses. Well, that's a little better. It's my fault. I chose a number to the 6th power. I should have done this like the 4th power. Anyhow, okay, so you can see that 15 times itself 6 times, a positive 15, is going to be plus. That's going to be a plus, so it'll be negative, whatever number this becomes, 15 times itself 6 times. Whatever the number is, it's going to be positive, right? This number is going to be a positive number. It's going to be a positive number, and then it's going to be negated by that negative on the outside. So this one's going to turn out to be negative. That's what I want you to see. So this one will, the answer will be a negative of 15 to the 6th power. Now what about this one? You multiply these two 15s times themselves, that's going to be a positive. Multiply these two 15s, it's a positive. We multiply these two 15s, it's a positive. See, so the answer over here, whatever it is, it's going to be basically 15 to the 6th power, even though it's a negative. It's going to be a positive number. So it's going to be the value of 15 to the 6th power, and it's going to be positive. And on this side, it's going to be to the negative. Okay, I knew you wouldn't be satisfied with that. So I've gone and multiplied it out. 15 to the 6th power, or 15 times itself 6 times, is 11,390,625. Notice on the left side it's inside brackets, and on the outside of that is a negative. So that would make the number a negative 11,390,625. But on this side, because these are all pairs of negatives, and a negative times a negative is a positive, this number becomes positive. So it's positive. It's positive 11,390,625. So they're way different than each other. So the answer is false. They're not equal to each other. So here's the deal. If you have a negative number, say like negative 3, and it is to a positive exponent, to a positive power, it's going to have a whole bunch of pairs. In this case, it would be a negative 3 times a negative 3, which would be 9, positive 9. If you had an odd number, negative 3, and that has to be in parentheses because the exponent only goes to the thing, to the base. And this, well, just did that wrong. In this case, the base is that whole parentheses. Okay, so here, if I do it to the 3rd power, that equals negative 3, negative 3, negative 3 times itself. So these two, that gives us a positive 9, but we multiply it times another negative 3, and we're going to get a negative 27. See, so if the exponent is odd and then the number the base is a negative base, you're going to get a negative answer. If it's even, you're going to get a positive answer. But that, remember, it's just talking about the base, though. So if there's a negative on the outside of this, you see, then that still would be a negative 9 because the answer would have been 9, but a negative on the outside would make it a negative 9. Okey-doke. So now you can go back and see that this 6 only has to do with this 15, not the negative. This 6 does the whole thing. It's even. So these are all pairs of positives. Well, this ends up being negative. So our answer again is false. Number 19, find the opposite or additive inverse. So the additive inverse or opposite is the number that if you add it to 28 in this case 28.7 would make it 0. So 28.7 plus a negative 28.7 will equal 0. So that's the opposite or additive inverse. Another way of thinking about it is 28.7, let's say it's out here, 28.7. The opposite or additive inverse would be on the opposite side. It would be a negative 28.7. The opposite, for instance, of a negative 11 would be a positive 11. Opposite or additive inverse, see, because negative 11 plus 11 equals 0. Number 20, find the decimal equivalent of 2/9. Now the way we find equivalent means what it equals to as a decimal. Alright, so the way you change a fraction into a decimal is you divide the numerator by the denominator. So 9 into 2. Okay, so we're going to have to add some zeros. Put the decimal point there, and we put it straight up, right? Decimal point there. Add a 0. 9 goes into 20 about 2 times. So 2 times 9 is 18. Subtract, we get 2. Bring down another 0. 9 to 20 goes 2 times. 18. 2. Bring down another 0. 2. 18. You can see that this is going to go on forever. See, so the way we write this, the decimal equivalent for this, is we can't write the infinite number of 2's that would go there. So we just write 0.2 with a line over it, and that means those 2's repeat. And this is also showing that it's a rational number because that's a repeating decimal. The only other kind of decimal you get that will be a rational number is one that terminates, like 1/8. If you divide 8 into 1/8, decimal point up there, right? You get 1, 8, 2, 8 into 20 goes twice, 16, get 4, another 0, bring that 0 down, that's a 0. Okay, 8 into 40 is 5, 5 times 8 is 40, I don't have room for it, but you see, and it ends there. That's it, 40 minus 40 is 0. So you get 0.18 equals 0.125. So with some fractions, you're going to get a repeating decimal like this one, and for some of them, you're going to get a terminating decimal like that one. Number 21, use all applicable terms to classify the given number. So notice it gives us the sets. It's not saying sets, it's using these terms, and it's giving you the terms. So it's a natural, whole, integer, rational, irrational. Natural numbers, whole numbers, integers, rational numbers, or irrational numbers. The only one it doesn't have in there is real numbers, which all of these belong to. So we've gone over this before. It's not a natural number because it's not one of the counting numbers, 1, 2, 3, 4. It's one of the whole numbers, so it would be whole, and it's an integer, and it's a rational number. But it's not an irrational number. No. But it would be a real number, but they don't have that listed. Well, I'm going to throw it in anyway. Number 23. Insert the symbol less than or greater than to make the statement true. The absolute value of a negative 3.3 is it what? Is it less or greater than a negative 6.8? Okay, so this absolute value thing, we have to know what that means. So let's draw a number line in here. Absolute value, these two straight lines, tells us how far something is from 0. So if we have a negative 2, which is right here, that's 2 from 0, so negative 2 equals 2. So a negative 3.3, which would be right about here, well, that's 3.3 from 0, so absolute value of a negative 3.3 equals 3.3. So when you have an inequality, you kind of want to figure out what's the actual value of the things on either side. So what we have here is actually positive 3.3. And what is it compared to a negative 6.8? Well, negative 6.8 is way over here on the scale, right here. So that's a lot lower than a positive 3.3, which is right here. So this is a greater than. Notice the wide part of the greater than symbol goes towards the larger number, the number that's greater. One additional thing is there's a difference between opposite and absolute value. Absolute value is always a positive number. Absolute value is always a positive number because it tells us the distance from zero. Like when we talk about below sea level, for instance, below sea level, we actually are using absolute values because we say, oh, 2 miles below sea level, like where the Titanic is, or 5 feet below sea level, or if we say above sea level, 5 above sea level, you know. And we're always using absolute values, how far it is from zero. Or when we talk about how much money we owe, we actually use absolute values. I don't say I have a negative $100, I say I owe $100. And same with temperature. We'll say that something is so far below zero, or so far above zero. So we're using absolute values there. But there's a difference between that and opposites. Sometimes the absolute value is the opposite. So when the absolute value of a negative number is always its opposite. But the opposite of a positive number is a negative. Absolute value of a positive number is also positive. See, so you have the absolute value of 6, that equals 6. Absolute value of negative 6, that also equals 6. However, the opposite of 6 is a negative 6. The opposite of a negative 6 is 6. So it's different than the absolute value. See that? But anyway, here they want us to insert which of these symbols. And this one is 3.3. The absolute value of negative 3.3 is 3.3, and that is greater than a negative 6.8. Number 24. Use the distributive property to rewrite the expression. Now, there are about three or four different things going on here. We've got the distributive property, we've got fractions, and we've got unlike terms. So I think I need to go over each of these things just momentarily. So why don't I'm going to go to problem number 31. Number 31 says, combine like terms. Now, so we have 8a minus 6a plus 2. So 8a and 6a, negative 6a, are like terms. So let's talk about like terms and unlike terms first. Numbers, 2, 7, 25. Well, those are all like terms. We can add them together. But we can't add 2 plus x because we don't know what x is. X could be a million. It could be 0. It could be a lot of different things. So if we combine that, somehow we combine that 2 and that x, we're going to get the answer wrong. So we don't do that. That's an unlike term. Also, x plus xy. We can't combine those two terms because we don't know what x and y are. So x could be 0 and y could be a billion. X could be 500 and y could be 3. You know, so there's no way we can combine them. We can do some things like if with x plus xy, we could actually factor out the x. So this would be x times 1 plus y. These two things are equal, which I'll show you later when I talk about distribution. But we can't do the other. If we have x plus x squared, well, you look at that and you think, oh, I could combine that. No, you can't. You can't combine them because let's say if x was 1, then we'd have 1 plus 1 times itself 2 times is 1 times 1 is 1. That would equal 2. But what if in x plus x squared, x was 100? X was 100 here, and then that was plus 100 times 100. So we've got 100 times 100 is 10,000. It'd be 10,100. Yeah, 10,000. Do that right. 10,100. You see, there's a really big difference between 2 and 10,100. So we cannot combine variables with different powers, unless we know what the numbers are. We know exactly what the numbers are, that's fine. So in this case, number 31, we have 8a minus 6a plus 2. The like terms here are 8a and 6a. They're different than the 2. The 2 is an unlike term. So we can combine these two. So there's 8a's. It's like, let's say that there are 8 apples. And then we're going to subtract from that 6 apples. Well, we can do that. And then let's say there's plus 2. Well, we don't know what the 2 is, see? So we can subtract the apples, but we can't do anything with the 2. So 8 minus 6 is 2 apples plus 2. Okay, so over here with our a's, 8a, by the way, 8a means 8 times 8, just like the 8 apples. 8 times 1 apple is 8 apples. 8a, so these numbers next to the letters mean that's how many of them you have. In this case, it's a negative, so that's like a debt, like you owe 6 apples or something. Okay, so it's convenient that it's a, and I can talk about apples. Okay, so 8a minus 6a plus 2, we can combine these two, and we get 2a plus 2, and that is all we can do with that. Okay, then there's that aspect of the distributive property. What the heck is the distributive property? Well, the distributive property says that if you have a and it's times a parentheses, which has b plus c in it, that will equal a times b plus a times c. Also, if you have a outside of parentheses that's got b minus c, you get something similar. You get a times b minus a times c. So that's something you need to get used to. So, for instance, I'll prove it to you that this works. Let's say we have 2 times 3 plus 4. Okay? Well, that would mean 2 times 3, that 2 times 3 plus 4 would equal 2 times 3 plus 2 times 4. Let's see if it does. Okay, 3 plus 4 is 7. We have 2 times 7, that's 14. Okay, over here 2 times 3 is 6. 2 times 4 is 8. 8 plus 6 is 14. So that works. What about if it was subtraction? What if we had 2 times 4 minus 3? Well, then that would equal 2 times 4 minus 2 times 3. I got it in there. Okay, so 4 minus 3 is 1. 2 times 1 is 2. Alright, 2 times 4 is 8. 2 times 3 is 6. 8 minus 6 is 2. So you see, it works. So if we had a problem like 3, let's make it a negative 3. Negative 3 times a negative x plus z. Let's use a different letter. So negative 3 times a negative x plus z. Alright, so when we distribute, we're going to multiply this times this one, and this times this one, and then we'll use the sign between the two products. Okay? So a negative 3 times a negative x is, negative times a negative is a positive, it's going to be positive. We get 3x. Okay, and then we have a negative 3 times z. So the z is a positive, the 3 is a negative. We get a negative 3z. And that's all we can do with that, because we just saw that these are unlike terms, right? The z and the x, we don't know what the z and the x are, so we can't go any further than this. The only other thing we can do is take the negative 3 back out, or just take a 3 back out by factoring. Okay, so you're saying, oh, all right, combine like terms, that's easy enough. Just derivative property, oh, that's simple too. But what about the fractions? What do we do with this fractions? This negative 4/5 times this parentheses with negative 5x and the positive 10y. How do you multiply a fraction times a fraction? And then how do you multiply, or a fraction times a whole number for that matter? Or how do you multiply a fraction times a bunch of variables? You know, what the heck do you do there? Well, I guess I'll have to show you. Let's say we have 2/5 times 15. Okay? If we're going to multiply 2/5 times 15, then we have to make a fraction out of the 15. So we're going to get 2/5 times 15 over 1. And then we can do cross canceling if you know how to do that. Divide the 5 into the 5 and a 5 into the 15. We get 3, we get 1. 3 times 2 is 6. That would be over 1. The answer would be 6. Or if you don't cross cancel, we have 2/5 times 15 over 1, which would be 30 over 5. And 30 divided by 5 is 6. Okay, so we get the same answer. Okay, simple enough. But what if it was a negative 2/3 times a positive 9? Oh, we can't do fractions with negatives, can we? Of course we can. The answer, the negative times a positive, is going to be negative, right? So we could just put the negative over here if we want. And we'll turn it into a fraction, cross cancel if you can stand it. And we get a negative 6 over 1. Oh, again. Or a negative 6. Right? If we had a negative 1/2, let's say they're both fractions. Oh, let's do it this way. A negative 1/2 times positive 6. Alright, we'll do that. Okay, make that a fraction. Our answer is going to be negative. Okay, so put the negative over here. 2 into the 6 is 3. 3 times 1 is 3. The answer is going to be a negative 3 over 1, or just 3. Okay, no problem. What about negative 2/3 times 12x? What do we do there? Well, the 12x means 12 times x, right? So, I mean, if you want to think of it this way, you can say it's 2/3 times 12 over 1 times x, right? So we'll do this. Actually, there's the associative property allows us to do that. Since we have that, we can because here these are associated, right? Well, the associative property allows us, when in multiplication and in addition, to group whatever that we want. As long as everything is multiplied times itself or everything is added, we can group and deal with one part or another. It doesn't matter. So this allows us to multiply the numbers times the numbers and the letters times the letters. If we have more letters, more variables in there. So here this simply becomes 3 into that is 4. Okay, so negative 2 times 4 is a negative 8. So that would give us a negative 8x. So after you do that enough, you realize you don't even have to separate the numbers. We'll go negative 2/3 times 12x. Okay, I'll put that over 1. I'll just cross cancel, or let's say I don't cross cancel. I'll make that a negative 24x over 3 will give us a negative 8x. Same thing. Or, remember I was saying before, put the negative on the end. See, when negative 2/3 either equals a negative 2 over 3 or it equals 2 over a negative 3. Because remember, this fraction bar thing, that means divide, right? So a negative divided by a positive, or a positive divided by a negative, is a negative. So hence, oops, it's erasing everything. So we could just make our answer negative and multiply the 2/3 and get, 8x, 2/3 times 12x and get negative 8x. Or we can make the 2 negative or the 3 negative. It doesn't matter, one or the other, right? So let's oh, now it won't erase. All right, so, well, I can do it this way. Now let's make the 2 negative. In this case, if we you can still do the cross canceling. Well, let's say you don't, okay? Then we get negative 24x over 3, which equals, and then 3 into the 24 is a negative, into a negative 24 is a negative 8x. Notice we keep getting the same thing. Or, let me do it up here, we'll make it 2 over a negative 3. Because remember, it equals all three of those things. 2/3, negative 2/3 equals either a negative 2 over 3 or 2 over a negative 3. It does not equal a negative 2 over a negative 3, because you can see that that would be positive 2/3, right? So don't do that. It's got to either the top or the bottom. It's got to be negative. So if I did 2 over a negative 3 times our 12x over 1, let's say I cross cancel, okay? So negative 3 into the 12 is a negative 4. 2 times a negative 4 equals negative 8x. I keep getting the same answer, you see? That brings us back to our original problem. So this has been a long problem, but all this stuff was important. Okay, so we've got a negative 4/5 times a negative 5x plus 10y. Okay, so our negative 4/5, I'm going to write it big, use up all my space as usual, plus 10y. Okay, so we're going to, this distributive property says we multiply this times both of those. Just because it's a fraction doesn't mean we don't keep following the same rules we did before, distributive property. Okay, so we can take these over on the side, make a line here. Take each of these multiplications over on the side. I've got negative 4/5, which remember could be a negative 4 over 5, 4 over a negative 5, or just the whole thing is a negative 4/5, right? And that's going to be times a negative 5x over 1. So it's a negative times a negative, so the answer is going to be positive. You can either think of it that way, or you can make your numbers, one of the numbers negative of your 4/5 and work it out that way too. Okay, for those who don't like to cross cancel, we'll just not cross cancel on this one. But the answer is going to be positive. So we'll just go 4 and we'll get 20x, because 4 times 5 is 20, 20x over 5. And 5 into 20 is 4. So the answer to that is 4x. Okay, for the first one. So we'll put that in there, 4x. And now we'll do this other one on the side. We've got a negative 4. Whoops, didn't want to do that. We've got a negative 4/5 times 10y. We'll rewrite it. Negative 4/5 times 10y over 1. Now we've got a negative times a positive. So the answer is going to be negative, right? I'm going to cross cancel on this one. 2. Keep the y though. I didn't cancel out that y. 5 into 10 is 2. 5 into 5 is 1. Okay, 4 times 2 is 8. And still the y. Can't forget our y over 1. Or it's a negative 8y. So minus 8y. We're done. It's a long answer to actually a rather easy problem once you see what we're doing here. You just take a piece at a time. It's not so hard. So we go that negative 4/5 times negative 5x and the negative plus, and plus the answer to negative 4/5 times positive 10y. The end. Okay, number 25. 56 hundredths, or 0.56 times 1,000. Okay, so 1,000 is a power of 10. And multiplying by powers of 10 is actually very easy. We just have to move the decimal place as many times as we have zeros. And multiplying something by 1,000 is going to make it bigger, right? So we're going to be moving the decimal point in the direction that makes the number bigger. So if we have 0.56, we're going to move the decimal place and use these loops. There's whoops. 1, 2, 3. Right there, and put a 0 there. So the answer to this is 560. So in general, multiplying by powers of 10 is about moving decimal place, the decimal point. And if you're dividing by powers of 10, you're moving the decimal point in the other direction. You're making the number smaller. Here's why. Let's say we have 0.56. We multiply times 1,000. What would we do? Well, 0. We put that 0 in. Put that 0 down, and put that 0 down. Then we multiply by 1, and we get 56. And then we have 2 decimal places. We put it right there. You see that? See, so this is just a shortcut. If we multiplied, let's say we multiply, well, let's just use 56, 0.56, all right? So if we multiplied that times 10, we would get 5.6. You notice we moved the decimal point one place. We multiply it by 100, we move it 2 places, 56, times 1,000, 3 places, 560, by 10,000, we move it 4 places, be 5,600. Notice this 0.56, moving it 4 places, 1, 2, 3, 4, put the 2 zeros in there, and you notice same thing. So when you're multiplying by powers of 10, you move. Notice that if you multiply it by 1, for instance, which is the multiplicative inverse, multiplicative identity, it's going to stay the same, right? There's no zeros there, so it stays 0.56. Okay. Okay, so what if we're multiplying a number like 0.32 32 hundredths by a power of 10 that's less than 1, like 0.1, 1/10? Well, it's like we would do it longhand times 0.1. We would get 32, and we'd have to have 3 decimal places, right? Because there's 1, 2, 3 of them. So the decimal point, we'd have to move it 3 places. 1, 2, 3. 0.001. So multiplying 0.32 times 0.1, we're going to move the decimal place 1 time. We have to have 3 decimal places, 0.032. If we multiply 0.32 times 0.01, well, the answer would be have 4 decimal places, 0032, and so on. And actually, it's the same as if we were dividing, because 0.32 times 0.1 is the same as 0.32 times 1/10. Okay, so I'm multiplying by 1/10. That would give us 0.32 over 10, right? We'll put that over 1. I know it's a decimal, but hey. Okay, and so that 0.32 divided by 10, see, it will give us the same thing. It'll give us 0.032. So every time you divide by a power of 10, you go in the other way with the zeros. If you divide by 10, you're adding 1 decimal place, 1 more decimal place. Divide by 100, 2 more decimal places, and so on. You want to practice this just to get used to it, but it's very easy. That's the beauty of this base 10 system we have. Everything's based on 10s, so we can just move decimal places. Okay, so 120 and 1,031 10,000ths, or 120.1031, divided by 100, I've already explained how to do that. We move the decimal point. We're dividing now, so we're going to make the number smaller. We have 2 zeros. We're moving the decimal place 2 points. So we move it 1, 2. So our new decimal place is right after the 1. It would be 1.201031.